Okay, welcome everybody. It's my pleasure to introduce Alcides Buss, who is going to talk to us today about free actions of groups on separated graphs and their C-star algebras.
Okay, so thank you, Tristan. Thank you, everybody. Thank you for the invitation. So I'm going to talk about this should say first, is joint work with Pereira and Adu Dalla Costa. So this project started a long time ago when I visited Peri in Barcelona, more or less 10 years ago already. So at that time I was doing some work with related to free actions, or more specifically proper actions and generalized fixed point algebra. I was in Germany working with Siegfried, and then I came to Barcelona. We started discussing these things, and I'll point out in a certain point how this relates to this. We don't need actually to relate it, but it's related to this theory of fixed point algebras. Okay, and you see, so, and we are going to consider actions on separated graphs and describe the C-star algebras somehow. So let's start by recalling the standard, so the ordinary case of graphs. And then I move slowly on to separations also. I add this stuff. But now let's, so for the whole talk, actually, so we have a free group. Sorry, we have a discrete group, and sometimes it will be also a free group. But so when usually we denote it by G. And then we have a graph, directed graph, so we can assign a C-star algebra. And we say that the group acts on the graph if it acts on the vertices, it acts on the edges that denote by E0 and E1. And this should be, of course, compatible with the graph structure. And this is in the way that the source and range map are equivariant. So this is the way it should be compatible. So this is the notion of an action on a graph, a discrete group acting on a graph. And we say that the action is free. We are interested in free action. And if both actions are free, and this actually is implied already by freeness on the vertices because of the existence of this equivariant map. So how do we get examples of those things? So one very trivial way to build such actions, free actions, is to take the very obvious things, like we take a graph and we take the group itself. We fix a graph, any graph and any group, and we take just the product. So we actually view the group itself as a trivial graph where we only have vertices, elements of the group, and just loops, identities. So this means that the source and range maps on the group level are just the identity maps. And then we just take the product of all the structure, and this gives a new graph. And this carries free action because the group always acts on itself by translations, and this action is always free. Yeah? So this is a trivial way to build examples, but we are interested in modifying this trivial example, but to get more interesting ones. So for instance, these products, they usually be disconnected graphs. So we usually don't want to deal with disconnected graphs. This will add direct sums to the C-star algebras. So in general, we are going to then join different edges by different group elements. And so for this, we need another piece of structure. As before, we have a group and we have a graph. But now we add a third piece, which is a function, just a function from the edges to the group. This is we view as a labeling. So we are essentially labeling the edges by the group elements. So and then, as before, we can take the product, but now we modify the structure. We actually, the source is as before, is just the source times identity. But we change here, for instance, the range map. So we could also change the source. It would be a different convention, but for us here, it was better to change the range. And we also have different ways to change this. We can multiply from left or right, but since we are going to look at translations from the left, we are going to multiply from the right by the edge, by the labeling. So here we modify the range in this way, where we multiply by the labeling from the edge E, from the right. Yeah. So this gives a new graph, and this graph then still carries an action of the group by left translation. This doesn't destroy the structure because we only multiply from the right, and now we can act from the left, from the group, still get actions, free action. So here's a simple example where we can do this. For instance, we take a graph only one vertex, V, and two edges, so two loops. Yeah. So in this case, we can, for instance, take the integers and define labeling one of the edges by 1 and the other edge by 0. Say the F is labeled by 1 and the E by 0. Yeah. So we assign this function, this labeling function, and then we can build this Q product graph, and this it will look like this more or less. So since we are labeling the edge E by the 0, which is the neutron element of the group, we are only going to repeat this loop infinitely many times. We are, of course, create new vertices. We take the single vertex and take the product. So we have a new vertex for every group element. And then we are creating the loops as before, they remain there, but we now connect the F, since the F receives the label 1, it connects actually one of the vertices to the next, so it gets connected then to the next level, so to say. This is a nice connected graph. So one can get, for instance, examples like this. And there is another example here that comes very naturally in this context, which is the following. So we can take a group, we can take any group which is finitely generated, and we say any generators. And then we can build a so-called Cayley graph of this group, which is the graph which has vertices are the elements of the group. The edges are elements of the group times the generators. And the source, you can recognize some similarity with the previous construction. So the source is just essentially doesn't take account in the generators, but the range, it multiplies by the generators on the right. So you can more or less imagine that this is indeed a skew product. And indeed it is a general result that I'm going to explain in a moment, the Gross-Tucker theorem. But in this case, one can actually describe it directly by proving that this Cayley graph is indeed a skew product. It's the skew product of the Kunstgraph. The Kunstgraph, I mean, I take only one vertex and n loops. This is the graph that gives the Kunst algebra ON. And we take the labeling where we take any loop and label it by a generator of the group. And then if you build this Q product graph, this gives exactly up to isomorphism this Cayley graph. Okay. So we can apply in particular our theory later for this graph. And the result that I mentioned is the Gross-Tucker theorem. It actually gives a description of how free actions on graphs and says that how they are isomorphic to SQ product. So this is a particular case of this general result. There is a book by Gross-Tucker where they prove this in a slightly different language from graph theory, and but the result is from Gross-Tucker, and they prove that given any free action of any group, discrete group on a graph, it is isomorphic to a skew product of as exactly as we described. So and how you build, so here I'm calling the graph F that carries the free action, and this graph will be isomorphic to a skew product, and the graph that you find by the Gross-Tucker is always the orbit graph. Whenever we have a free action, whenever we have an action, we can build the orbits, and these orbits are exactly the graph here that we find in the Gross-Tucker. Yeah. And of course, one has also to choose a function as a labeling, and then one has to choose this conveniently to give this result. Okay, so this means that if we want to study free actions on graphs, this theorem says that we can equivalently study these skew products. So studying free actions of groups on graphs is essentially equivalent to study skew product graphs. So in particular, we say want to understand the system algebras of free actions on graphs or system algebras of those graphs. We would need to understand the system algebras of these skew products, and somehow we would like to relate, of course, these to the original system algebra of the graph. Like we had in this example, the Kunz graph, this gives a Kunz algebra and so on. We can apply this to this situation. So in this situation of ordinary graphs, this has been done first by Kumjan Pesk, for at least 4 billion groups. They did these 4 billion groups, and then they proved that every labeling gives an action of the dual group, and then describe the system algebra as a cross product of the dual group on this system algebra. And later it was recognized by Kalizewski and Quick that actually this is an instance of a more general result when one can relax this abelianness of the group by replacing the dual action by a co-action of the group. And this is, we are going to extend this result. That's why I do not put this result here at the moment, but I'm going to state a more general result that includes this here for separated graphs. Okay. But there is a way well known to describe this system algebras in terms of the original algebra and a certain action or coaction. Okay, let's now move to separated graphs. I want to add this new piece of structure and then study similar things, actions on those things. So let's first define what a separated graph is. So a separated graph is just a graph as before, a directed graph. And now we add a separation. We are usually going to view this again as a labeling or a coloring of the graph. We are going to coloring different edges, and this will change also the system algebra, the relations that we impose. So essentially, it's a graph coloring with a coloring on the edges. So formally, this is a partition of the edge sets the edge set. So we partition actually each set of pre-images of a vertex V. So we look at all edges departing from V, and then we look at all those edges and color one of the edges, say, is blue, the other part is red, and so on. So this is just a partition of this set into different pieces. Yeah? So this is just a separated graphs. And just for technical reasons, we need some finiteness conditions at some point. So we say that this separation is finite or finitely separated if the sets of the separation here, the sets inside this partition are finite. Yeah, it's just a technical condition. And usually, even if you just restrict to finite graphs, it's okay. So we have many interesting examples here, but of course we don't want to add this condition because we are going to usually take infinite groups and take these Q products, and they are not finite. So we don't want to add finiteness of the graph, but the separation we need at some point to be finite. And then as for ordinary graphs, one can define a system algebra. This was defined by Pereira, I should say, and Gouder. They studied these separated graphs and they assigned to them algebras over fields and also system algebras, complex system algebras. So this is very similar to the usual graph system algebras, if you know those. And so it's a universal system algebra generated by mutually orthogonal projections that we usually call PV, or usually people also just call them V, confuse it with the vertices. And also we have partial isometries for each edge. And we have some relations that we want to impose. This first relation is the usual one as for ordinary graphs. So this depends on some convention, depends whether you want to view from the graph point of view or from the group point of view. Maybe you change here the source, but the range. But here we are taking this convention that looks at the graph convention, essentially the way we walk in the graph. So this means that the range projection of this partial isometry is the projection associated to the source. So this is a bit strange for some people, but this is also used as one of the conventions. And we are going to take this convention. Okay, this is the usual one. The second is also required that essentially in the graph, all these partial isometries they are sort of mutually orthogonal in this sense. But here is the first difference. We only require that they are zero here for different edges, E and F, if they are in the same set of the separation. If they are in different sets of, if they have different colors, we don't impose any relation. So this is then not zero, so to say. And also the last condition is the sometimes called the Kuntz relation. It's the same also as for ordinary graphs, except that we only look again at edges in the same set of the separation. So essentially we have here inside X, if you only look at X, we have the graph system algebra, but we take different, many different of those sets, and then the only thing in common in all these things are the projections that they leave in all these things. And essentially the edges, one has to separate them and then only look at relations that are inside for the same color, for the same set of the separation. So just to emphasize again, so these elements need not be zero in general in these system algebras. So this makes these system algebras much more complicated to describe, of course. And in particular, if you want to just describe some basis elements, some elements that you can work, yeah, in this system algebras, some generators. So you need to multiply also those things that in general are not zero. So in the usual graph, we would only have things like this here, a path of length 1. In general, in this separated graph system algebras, we need to also consider this product. So we, in general, we are going to have this, follow it by another thing like this, and so on. And we, of course, we could also start with a star here, and so on. So essentially, we have linear spans of products of those elements, and then the closure to build this system algebras. And then it gets much more complicated because of the length of this path that can get very complicated. Okay, and one can put these paths in a certain reduced or normal form, but one cannot do too much. So it's really quite complicated in general here. So to just give an example and for you to get a feeling of how these system algebras can appear, let's look at a very elementary example. So we consider this graph here. So here in this picture, it says, should say everything essentially. We take here two vertices, V and W, and we take between these vertices many edges. Some of them we call I's, and some of them Fi's or Fj. We have different numbers here. In my picture, we have 3 reds and 3 blue, but we could have 3 reds, 4 blues, or any other number, respecting actually only these things here. So the number of F's is always smaller than the numbers of E's. So the red colors are possibly larger. And they could be equal, but this is the structure. We just have 2 vertices and many edges between them, always coming from V to W, and some of them are red and some of them are blue. And one can then prove that this system algebra is up to matrices, so in particular up to Morita equivalents. The universal system algebra generated by a unitary rectangular matrix. So we know that in non-commutative algebra we can have a rectangular unitary matrix, and this, if we assign a system algebra or an algebra to this is related to this graph. And this algebra was studied before by Brown and McLachlan, and this is usually called this UNN. In particular, here we have also the Kunz algebras appearing. If we take here M to be equal to 1, if we only have one blue edge and many N red edges, this actually here is exactly the Kunz algebra that appears here. So it's a generalization of the Kunz algebras, these algebras here. But they are much more complicated. They are not exact. In general, these are not classifiable system algebras, so to say. Okay, but they appear as those algebras. Let's look at another example related to these previous examples of this Cayley graph that we had. So we have the Kunz graph. Let's look at the Kunz graph. So the Kunz graph is just one vertex and many loops, yeah, say any loops. One can assign the system algebra will be the Kunz algebra, but one can also separate this graph. So we can introduce separations, and then it depends. You can build many different separations. Oops, sorry. For this, my handy is hanging on my, sorry. And then what we do here is we consider the finite separation, where we have for each edge, each loop, we assign one color. So we we color one of the edges, say blue, another red, another green, and so on. So we gave a different color for each edge, and this gives a separated graph. We can look then at this system algebra, and if you think of the relation, so we isolate each loop. So in the relation, we are going to say that these loops are going to give unitaries, because this Kunz relation is just for this separation. So what we are going to get for the system algebra is just the universal system algebra generated by any unitaries. And this is the system algebra of the free group. So this is isomorphic to the system algebra of the free group on n generators. In general, we can also separate these loops differently. Of course, one can take some, say, 2 or 3 of these loops and color red, other 3, 2 or 4 loops we can color blue, and so on. So we can take a partition of n in different sizes of integers and so on. So in general, we are going to have here is Kunz algebras, but different of different sizes essentially, and they don't talk essentially to each other in this algebra. So what we get is actually a free product of Kunz algebras in general for those system algebras. Okay, so you can imagine here these system algebras also are not in general not nuclear, for instance. Actually, there is only one thing that gets the same in all this algebra, which is the vertex. The vertex is common to all these algebras. So this means that what we take here is actually amalgamated free product over the unit. So unito amalgamated free product. Okay, and actually this is what happens in general. So this structure of this graph system, this separated graph system algebras, they are can always be described as free products of usual graph system algebras. So what happens is the following. So we have for each one of these sets, we have we can build a subgraph, which we only look at the edges which have this color, so to say, this color X, which are the edges belonging to this set of the partition. And then we take out the vertices for this, and then this builds a subgraph. We only look at the edges living in this set of the partition. And this subgraph gives us subsystem algebra, which is the usual graph system algebra inside the separated graph system algebra. And what is common, so if you look at the relations, you can prove this by the universal property, essentially, that this is isomorphic to this, essentially. The only thing in common is the projections which live in all these algebras. And so this means we take an amalgamated free product over the projections, over the vertices, and this gives this system algebra. So this is a general structural theorem for those system algebra, and can use this to prove some things. But this is, of course, complicated. In general, we had some difficulties proving some results using this free decomposition here. So we need another way actually to work with these algebras. And in particular, you also want to, in general, this doesn't appear for ordinary graphs, but here, since these are not well behaved, maybe we can build maybe a quotient or quotients of these which are better behaved. And in particular, here we can assign a reduced quotient. How we do this? So here we have inside these algebras always these ordinary graph system algebras. And for ordinary graph system algebras, there are ways to build certain canonical condition expectations. I don't recall the formula here, but there is always for every, or essentially every, here is where we need some finiteness condition, row finiteness. For every row finiteness graph, we we can assign a certain canonical condition expectation. There is a formula for that. I don't want to give the formula here. It's not very important. It's just enough to know that there is a certain canonical condition expectation. And indeed, this is a faithful condition expectation onto the vertices. And then there is also a general construction. Whenever we have here conditional expectations from these algebras forming the free product, the amalgamated free product, one can take a sort of free product of these conditional expectations and build a conditional expectations on the free product. So in other words, we have what we call a canonical condition expectations on this algebra onto this subalgebra. Okay, but the problem is that maybe is not faithful anymore. So maybe not faithful. Yeah, this procedure of taking free products maybe adds some kernel to this condition expectation. And but we can always make it faithful. So to taking a quotient essentially by the ideal that it's the abstraction to be faithful essentially. So there is a general construction that we use a lot in this work to look at this reduced version. This was already known also before, so but we use this here, so you can use this in a very general setting. Whenever you have a system algebra and a subalgebra and you have a condition expectation, you can indeed do this for general condition expectations, but we are adding here a simplification. We say that symmetric. I'm going to explain this in the bottom here what this means, but essentially we take any condition expectation, we can build the largest quotient of A where this condition expectation factors through a faithful condition expectation. Yeah, so and this is done in the following way. So if we add this condition here, symmetric, this means actually that the left kernel is equal to the right kernel of the condition expectation. And one of these is a left ideal. This here on the left is a left ideal. This is a right ideal. So if they are equal, this is a two-sided ideal. So we can just take the quotient, and this quotient is exactly this reduced quotient. This quotient is the largest quotient of A that contains B and where the condition expectation factors to a faithful one. So in particular, we can apply this to our situation and build what we then call the reduced system algebra of the separated graph. And so the difference is that now we have a faithful condition expectation on this system algebra. And one can also describe this as amalgamated free product, but now a reduced version. So this was also studied before. And this has better properties. For instance, this is always now exact system algebra at least. The full one is not, but the reduced version is always exact whenever the components, of course, are exact, which is the case in here. So these system algebras are always exact system algebras, though slightly better. They are maybe not nuclear, so but slightly better. So these reduced quotients, they are slightly well behaved. More well behaved than the full versions. And for instance, one example is this one that we get the Kunstgraph and take this finest separation where we had the full system algebra of the free group. One can prove that the condition expectation in this case is exactly the canonical trace on the graph on the group algebra, and this then gives the reduced system algebra of the group as the system algebra, the reduced system algebra. Okay. Okay, we have then these sister algebras. We want to study then, or actually we want to study actions on them, and then relate these sister algebras to maybe other things. Okay, so now I need to first define what is an action on a separated graph. So as you should think is the obvious definition. So well, almost obvious. So we have an action on the graph, and it should be somehow compatible with the separation. So what we require is now we can move the vertices by the group elements. And so we translate the vertices, and if we have a set of the partition, we can also translate this set, and we just require that this is a new set. So it's again a set of the partition that gives the separation. This is the only condition. So it's essentially an action on the graph that permutes the sets of the separation. Okay, and then we prove so a structural theorem generalizing the Gross-Tucker that we call the separated Gross-Tucker here. This was our first result. So it's the analogous of the Gross-Tucker in the separated world. So we prove that every graph carrying a free action is a skew product. So I didn't define what is the skew product, but the graph part is as before. We take the skew product graph. And here I'm defining the separation. It's the most natural one. So if we take a separation on the graph E, we just then take the sets of the separation and then times the group elements, which are also edges of this graph. Yeah. So these are the separation, the sets of the separation. And then one can prove that every separated graph carrying a free action is of this form up to isomorphism. And necessarily the original graph is original separated graph is the orbit graph as before, except that now we add also the separation, which is also the orbit of the old separation essentially. Okay, this is then the first structure theorem, and then now we have the same sort of question. So we want to describe now the sister algebras of this, say we want to study free actions on separated graphs. So we want to understand that sister algebras by this theorem is then equivalent to study the skew product graphs, separated graphs, and then describe their sister algebras. Essentially, that's what I'm going to do next. So there is a first theorem, that's what I mentioned before for ordinary graphs, that we extend now for separated graphs. So what we proved, which extends these results by Kalizewski, Quick, and Kumjem and Pesk, they prove also there is a coaction, and we prove also a similar version for separated graphs, except that the proof had to be modified because of these complications. We need to work harder to prove the same results, but we achieved essentially the same result. So every labeling, now we take any graph, any labeling function. So it's essentially we are then looking at the skew product. We take any labeling, any separated graph, any labeling induces a coaction. So for those who don't know, maybe could think about an abelian group. This would be an action of the dual group. A coaction is just a homomorphism with some properties. And I'm defining how this acts on the edges and on the vertices. Yeah. So this homomorphism, it's on the generators, it takes an partial isometry of the edge and sends it to the same tensor. Here comes the labeling function. So the C of E is a group element that we view in the group sister algebra, of course. And this is how this homomorphism acts. And on the vertices, on the projections, it acts trivially or coacts trivially. It doesn't do nothing here interesting. So the only interesting part essentially is here, is where this labeling function comes in. Yeah. So, and there is an important property of this coaction, which comes from the fact that we are dealing with the maximal C-star algebra. This coaction is maximal. I'm going to explain in a minute what this means, yeah. But believe me now, so this is a sort of maximal coaction in some sense. And we also prove, so this reduced version in general is different. In the ordinary graph case, they would collapse and they would be the same. So there is only one result here in general. We need to consider also we would like to consider the quotient, the reduced one, when we prove the same result. So we prove that this coaction actually always factors through a coaction on the reduced quotient. And there, since this has a condition expectation, which is faithful, one can use this to prove that this coaction is a normal coaction, which could also be called the reduced coaction. It's another name for the same thing. But the formal name here that we use is a normal coaction. But this is smelling of, it smells like a reduced thing, yeah, in some sense. So I'm going to explain these both notions, maximal and normal, in a moment, but they had to do with these maximal and reduced completions. Okay, and then we also not only define these coactions, prove that they exist, we also then achieve our first goal of describing these Q products. So we prove that the C-star algebras of these Q products, both the full and the reduced, they are cross product exactly by these coactions. So the full for the full, here we take the full, and the reduced, we also take the reduced here. So if you take full and reduced in each case, we recover these C-star algebras as cross products. Okay, and for instance, to prove this here, the first one we use just the universal property, and the second one we use this lemma, use a lot the condition expectation to prove this reduced version. And the proofs are different in both cases. And we also have techniques to prove that they are maximal and normal, also using the condition expectations in the reduced case. But the corollary is now, even if you don't know these coactions, we could also give essentially the same result, or a dual equivalent, essentially equivalent result, but just talking about actions, if you maybe like this better. So we can take any free action on a graph. Yeah, we know that implicitly this comes from the Grosstocker. This will be a skew product. And we can describe then the cross product by this action. So I'm hiding here some things, but essentially we can prove that every action on the graph induces an action on the C-star algebra. And this also works for the separated case. And if we look at the full C-star algebra, we get this action, and then we take the maximal cross product for this action, and then we can prove that this will be Morita equivalent, or actually isomorphic, to the stabilization of the orbit separated graph, which is related, of course, to the Grosstocker, the structure of this Q product. So this is actually a consequence of this previous result and some duality result. And we have an analogous result for the reduced version. Yeah. And here's the point where I mentioned in the very beginning that this has to do with this fixed point algebras. One can read this result in terms of fixed point algebras. So actually, this result is essentially saying that the fixed point algebra of this graph here is the system algebra of the quotient graph. But actually here there is something here behind, so one has to prove, but it's not difficult to prove that this free action. So the point is that we have a free action of a discrete group on a discrete set. And whenever we have this, this action is already proper because stabilizers are trivial. And for every free proper action, we have a way to define the generalized fixed point algebras, and one can prove that actually these results are actually essentially equivalent to this here. Okay. And here is the diagram that that summarizes the main results that we have so far. So there are two versions. The version for the labeling, starting with a labeling function. So we take now, summarizing, we take any graph, any labeling, we form the skew product. And then on this skew product, we have this translation action, which is free. This induces a free and proper action here on the system algebra. And this actually, by the previous results, decomposes as this cross product by the coaction. And actually this action here on the left, this translation action corresponds to the dual action on this coaction cross product. And by using duality result, this going down arrow here is actually an isomorphism. This is also an isomorphism. This is the duality result. And this here is essentially the result that we proved on the left. And we can also, then we proved also the reduced version. This we can go down here. This is not an isomorph in general, going from the full to the reduced. But here on the bottom, we have our again isomorphisms here, similar to the full version. This summarizes these results for the coactions, and we can also draw a equivalent, essentially equivalent diagram starting with a free action. So we start with a free action. We can take the orbit, separated graph, and there we can take the coaction, take by the dual coaction, take the cross product, or we can go directly here via our result, and now this gets isomorphic, except for this one is just a quotient map. So the difference here from the ordinary case to the separated case is exactly at this point here, that we have two versions, and we might also have things in between. So one could also consider exotic completions here, but we didn't do this, only consider the full and the reduced. And now I come to the second part. I hope I still have some time, like 10 minutes or so, more or less. Tristan, how much time do I have yet?
Well, I mean, you've still got at least 7 minutes, but I mean, we're not very strict about this, so however long you want to go.
Okay, good. So I'm now going.
Sorry, just quick question before you go to the second part. So in the previous slide, when you pass to the co-action, you assume that G is abelian, or?
No. So if the group is abelian, then there is some simplification.
Yes.
For instance, what is the simplification? So these coactions, they are actions of the dual group. Yeah.
Yes, exactly.
And also you don't need to talk about maximal or normal, they are both. But actually, even if the group is abelian, this arrow still need not be an isomorphism, because this only depends on the graph here, whether it's amenable in a sense. But the group here is abelian, is in particular amenable. This gives some simplification, but still we have two pictures. I'm not sure whether this answers more or less your question.
Yeah, thank you. Yes.
Okay, so there is some simplification in abelian group, but not too much. It's only the case that these actions, they are both normal and maximal, but actually what is happening is that one is not the normalization of the other because of these different quotients that we are taking in the graph level. Okay, let's talk about now how this relates to Fell bundles. So actually the point is that coactions, they are always strongly related to Fell bundles. One can start with any coaction and build a Fell bundle. How this goes? So we take a coaction. This is just a certain group homomorphism, from some system algebra. We can build the following subspaces. We call this the spectral subspaces, and this, we, for instance, take the trivial group element, the identity. We are looking here at the things that are fixed by the coaction. In general, we take elements for which the coaction coacts as A tends to A tensor G. We saw these many, the definition of this coaction on the graphs, they are the generators, they coact exactly in this way by a certain group element that comes from this label. So there we have these spectral subspaces, somehow pieces of them. And but in general, for every coaction, we have actually these Fell bundles, and this reveals a lot of the structure of the Fell bundle of the coaction. And conversely, actually, there is a sort of equivalence between Fell bundles and coactions. If we start now with a Fell bundle, we can also build coactions that now depends on which completion of the Fell bundle you take. So you take the Fell bundle, you can take the direct sum and build a star algebra structure, and then you can complete both for the full or the reduced norm as usual. And in both completions, you get coaction. So these completions, they essentially contain the fibers of the Fell bundle, and then you coact in the fiber by sending an element of the fiber AG to AG tensor G. It's a sort of diagonal coaction. It's called dual coaction in general. Okay, and this, of course, generalizes the usual dual coactions on cross products. And here is one of the things that I promised before to explain what is this maximality and normality condition. Maybe the best way to explain this is to look at this Fell bundle, and actually then the coaction is maximal if the system algebra carrying this coaction is isomorphic to the full system algebra. This gives us smells of fullness of the system algebra. So essentially depends on how the system algebra is completed. So essentially from the Fell bundle, if it is the norm corresponds to the full norm on the Fell bundle, then the coaction is maximal. But actually the original definition of maximal coaction is a duality result here that takes the cross product and then the cross product again by the dual coaction, and then this should be Morita canonically, Morita equivalent or isomorphic to a stabilization of A. And similarly for the reduced or the normal case. So the coaction is normal if this norm on the system algebra corresponds to the reduced system norm on the Fell bundle, and this is also corresponds to a duality result. The difference here is that here we take the max and here we take the reduced cross product. Okay, so here is the explanation for these maximal normal coactions. And one maybe important remark is that, for instance, if we take the usual graph system algebras, we are in a situation where the system algebras we are dealing with nuclear. They are nuclear. In this case, one can prove whenever the C-star algebra we are correcting is nuclear, then there is no difference. That's why we don't see this in the usual graphs. So in this case, there is no difference, and this is related to amenability of the Fell bundle, of course, because if it happens that if the C-star algebra of a Fell bundle is nuclear, actually the Fell bundle is somehow already amenable. So this is related to amenability of the Fell bundle, okay? And here is then the result that describes, in our case, the Fell bundle. Yeah? So we can take now any graph, any labeling function. We can take any separation on this graph. We can build this coaction that we defined before. And for any coaction, we get a Fell bundle. And the point of this theorem here is to describe it somehow, to describe this Fell bundle. So if you remember the coaction essentially takes a generator like this and send it to the same generator times this here. Yeah. So this means that this here, this SE is in the C of G spectral subspace associated. So if we now look at paths or these combinations of paths that we have as generators, and if we extend, so we need to extend the labeling function to paths naturally. So we take paths and then take the product of the grouped elements. If you meet a star, we take the inverses. And if we extend in this way, and if this labeling of this path is a given element G, this means that this element is in the fiber G, so in the spectral subspace G. And this gives exactly the spectral subspace. So there is a small subtlety here, which is the norm here. So the closure here that we take is inside the C-star algebra. Yeah? So we can, okay, and saying that the coaction is maximal that we proved before, the coaction is maximal, now we can then conclude that the C-star algebra is the full C-star algebra of this Fell bundle. So this is a consequence of the previous result and this general result about maximality in terms of the Fell bundle. And this result in particular gives a Fell bundle structure for those C-star algebras. Yeah? So it depends on the label you choose, of course. Everything depends on this label, but for every label you choose, you get a Fell bundle and you get a canonical isomorphism. So this means that all these C-star algebras, I'm going to explain a very canonical label that one can take in a minute. They can always be written in this way. So this is a nice consequence of these results that we have. So we can describe the C-star algebras, at least the C-star algebras of Fell bundles. So the C-star algebras, as we are already indicated, they are sort of exotic C-star algebras. They are not exact, nuclear in general. They are not groupoid C-star algebras in general, at least not in a natural way, but at least they are sort of Fell bundle, non-commutative groupoid in a sense, if you view a Fell bundle as some sort of non-commutative groupoid. Yeah, we have a sort of dynamics here going on. And we have also a similar result for the reduced C-star algebra. We consider the reduced coaction here, the normal coaction. We can actually prove a very similar result describing the spectral subspaces exactly like this here before, but the difference here would be the norm. So we would take then the norm in the reduced. And since this reduced is a proper quotient of the full, we get an ideal. So this completion actually adds an ideal. So we are describing then the fibers in terms of this ideal. Actually, what you get is a quotient of the Fell bundle before that we had before. by a certain ideal, a Fell bundle ideal, and this Fell bundle ideal is strongly related to the nucleus of the condition expectation. You just take the fibers of the previous Fell bundle, you intercept with the nucleus of the condition expectation that gives the reduced, and this gives the Fell bundle. So this means that we have, since this coaction is normal, the system algebra is the reduced system algebra of the Fell bundle, of some Fell bundle, but this Fell bundle need not be the same. It's a quotient. So it's a reduced system algebra of a quotient, okay? And this ideal can indeed be non-trivial. So we proved, we provided some examples where this ideal is not trivial. So this ideal will be trivial if and only if this condition expectation restricts to only if these intersections are trivial, of course, and this is, it's enough to look at the unit fiber. This is a system algebra, and this means that this condition expectation restricts to a faithful one on this unit fiber, and this might not be the case. In some examples, it might be faithful there, but it's not in general. And yeah, so to finish here, so I want to consider a consequence here. So as I said, all these decompositions we get for every label, yeah. And in particular, so this depends on the label you choose. You can take any label, you get a Fell bundle, but this Fell bundle maybe is not intrinsically related to the graph structure if you choose arbitrarily some label that doesn't have to do anything with the graph. But there is always a very intrinsic label you can choose. You can apply this for every graph. You take the so-called free label, you call this the free label. We take the edge set, we need a group. What is the group we take? We take the free group of this set. So we take the edges and generate a free group from this set. And then we have, of course, the obvious map from the edge to the generators. This gives a label, this gives a function, and then we can apply our result. So this means that we can apply this for every graph now. We take any separated graph, we get this label, we get then this Fell bundle. This means that every graph system algebra, every separated graph system algebra is a full system algebra of a Fell bundle, which is intrinsically defined from the graph. And the same for the reduced. The reduced will be a quotient system algebra, the reduced system algebra of a quotient. Well, so let me just remark here that in the case of ordinary graphs, these system algebras, they are actually partial cross products. One can prove that these are actually groupoid system algebras. And this here is the reduced groupoid system algebra of the same groupoid. Here we are in a more complicated situation where these are not coming from groupoids, but at least they are Fell bundles. Essentially, in the graph case, we get the groupoid, which is associated to the essentially shift on the Cantor space and by the free group. It's a very natural partial action that one has. Well, I had prepared also some examples. If you want, I could go more or less quickly, or I could also finish more or less here. I don't know. If you want, I could go through this example. But if you are tired, I would stop. Maybe I quickly say some words about these examples. In these examples, they are very nice. So they are very simple from the graph point of view. We just take, for instance, this example here. We take 4 vertices and we have 4 edges, and we color them red and blue, 2 separations. Yeah. This is already very simple graph, but it's a very complicated system algebra that comes out here. So it's difficult to describe the whole cyst algebra, but we have a distinguished vertex V. Everything is coming from V. We can look at the corner from this vertex. We look at this corner inside. And this is indeed a full corner. So this is Morita equivalent. So describing this corner is actually essentially describing the whole cyst algebra. Yeah. And it turns out, this was proved by Periara and co-authors, that this corner is generated by a single partial isometry, which is in the graph here, which is essentially this thing here going from beta 1 and coming back from alpha 1, this sort of loop here that we have. This gives a partial isometry, and one can prove that indeed this cyst algebra, this corner, is the universal cyst algebra of a partial isometry, and this is the generator. So this means that in this cyst algebra, we essentially only have combinations of polynomials in S and S star, essentially. Of course, they did not commute. This is the complicated part. S did not commute with S star. So we need to take S star powers, etc. But here we have essentially a general element. And one can write every element as a linear combination closure of such, and then one can also add the condition that these do not contain the subsets of these, which are essentially the only relations, that this is S and this is S star. Yeah? So we can reduce this, but except for this, we only have these elements there. And then we can consider our theory. You can consider, for instance, the free label on this cyst algebra, and then we can restrict to this corner. And since this corner is only generated by this partial isometry, we have the corresponding group element. Here we have the free group on 4 generators. But in particular, we have this element here. This is special elements that generates this partial isometry. And actually it turns out that the fibers are supported in this element, because it's more or less reasonable that this is true, because the cyst algebra only sees this partial isometry. And this is then are the only fibers which survive. All the other fibers are 0. And actually then in this case, what we get is a integer grading for this algebra. We can sort of understand the pieces of this, in particular the unit fiber. It contains, for instance, elements of this form, but it might contain also other elements. It might be complicated to describe this better than this. But okay, we have this grading, and but we cannot say too much more if we only look at this. But to understand this better, we consider a companion graph, where we now consider a new graph. So before we had W3 and W2, we collapsed both to a single one. So essentially here we have one vertex less, so we only have 3 vertices, and we have essentially the same structure. This graph helps us to understand this previous one. So we can play the same game. Yeah, we can take the corner. This is a new cyst algebra, and then this new corner also has a structure, well-known structure. So Petty proved that this is actually a group cyst algebra. And the group that appears here is the so-called Lamplighter free version of the Lamplighter group. It's a strange free product here. So it's a group. It's the integer semi-direct product by the free product here. And then this can be described as a cross product by the integers, because this is a semi-direct product. And then one can play the same game, now define this partial isometry, and now we have another distinguished partial isometry. And actually this isomorphism here is related to the fact that the sum of these 2 partial isometries is now a unitary, and this unitary corresponds to the copy of the integers inside the C-star algebra. And then one can describe this isomorphism explicitly, find the copies of this group in there, but I'm not going to say to you more about this. But the point is that we can relate both algebras that we have, the previous one and then in this B, actually there is an embedding. So this B is larger than A. So there is a canonical embedding of one corner into the other. Okay. And what is nice is that all the structure is compatible. So in particular, we have here this canonical conditional expectation that restricts to the canonical expectation here. And the Fell bundle here that we get is actually the restriction of the Fell bundle above. And the Fell bundle for B, it turns out to be exactly this cross product here. So was associated to this cross product by Z. So things fit very nicely here. And also this is trace preserving. Here we have traces which correspond to the conditional expectation. And then from these one can prove, for instance, that this ideal that we get in general for our theory is not trivial in this case. And this is related to the fact that when we consider the trace and take the reduction, we look at the reduced C-star algebra of the group. And this is different in this case from the full. And then we get really a quotient which is different. So this ideal is not zero in this case. Okay, so this was what I had prepared. So thank you very much for attention. Sorry for over time.
Thank you very much. Very nice talk. So do we have any questions in the audience? If you have a question, just feel free to unmute yourself and talk.
Yep.
No. Doesn't look like it. Looks like you've blown everyone away.
Yeah. Yeah, this is a complicated thing, actually. As I already said, is algebras. It's maybe hard to understand in the first.
Yeah, there's a lot of different structures floating around, and yeah, various level equivalences and dualities and stuff. But yeah, no, it's very interesting. Okay, looks like Branimir has raised a hand. So
just a silly question. I mean, how much of all this structure sort of is already present at the level of the underlying, I guess, Levitt path algebra equivalence? Or is most of what's interesting that's happening only happening once you take C-star algebraic completions?
Yeah, this stuff that I talked about is only for the completions for the C-star algebras. If you look only at the Levitt path algebra, so you don't see this difference here. So actually, this, for instance, this grading structure that we had, this ideal vanishes there. So what I want to say is that the Levitt path algebra is essentially without before we take the closure here. Yeah, so we essentially, the Levitt path algebra can be described here as the span without the closure. And for instance, we didn't work with the Levitt path algebras, but one can probably prove also, at least this description here, I think we observe that this holds without the span. This gives a grading for the Levitt path algebra. And the point is that the Levitt path algebra, it lives inside both full and reduced. It's a subalgebra of both. Actually, this difference only appears if you take the completion. The Levitt path algebra, you would only get one single algebra, one decomposition, one algebraic Fell bundle. Somehow, I believe that you can prove this, but we didn't write this. But so answering your question, you only see differences if you go to the C-star completion.
But in terms of, I guess some of the, like this sort of the Gross-Tucker type results, like those kinds of structural results already, are they visible at the uncompleted level, or?
Yeah, so probably you can also prove, we didn't write this, but you can probably also prove similar results for the leverage on the level of the leverage path algebras. And this would probably be very algebraic. You don't need to use analytic methods for this. Probably we didn't write, so we thought about this at some point, but we didn't prove this result. We didn't write, but probably you can prove a result like the Gross-Tucker is just for the graph. Yeah?
Right.
It doesn't refer to the algebra, but I believe you can prove results like this. The algebra is also the free amalgamated product. This is just this general result. I think they observed this, Perry and Goodere. And I think you can also prove the result, this result that we have here. Let's see this result here. That if you consider the leverage path algebra, you can still consider this formula here. Yeah. And this probably gives a coaction in algebraic sense. And probably the algebra of this Q product decomposes as the cross product like here. But now as a Q like cross product, algebraic cross product. Yeah, you do
smash product or whatever.
Yeah. I believe that this is true, but this would require doing some things more algebraically, I guess. And then you would allow also fields which are not complex. Yeah. And some proofs, you need probably maybe some new ideas. I'm not sure, but probably it's possible.
Thank you.
Great. Any more questions? No, and if not, then well, let's thank the speaker again.
Thank you very much.
And next week we have Edwin Beggs, who will talk about differentiable positive maps, vector fields, divergences, exponentials, parallel transport, quantum mechanics, and state spaces. So we hope you'll join us online next week for that talk, which will probably be the last of the semester. So see you then.